Section 4.4, Linear Correlation. Alright, in this section we're going to look at the linear correlation coefficient r, which is of n data points, and it's one of the square roots of r squared, which we just saw in the last section. We say one of the square roots because numbers like 9 have two square roots, a positive 3 and a negative 3. And sometimes correlation is positive and sometimes it's negative, so we want to allow for both those possibilities. And you'll hear sometimes in the news them talking about a study that they found that one variable is correlated to another. And when they're talking about that, some synonyms for what they mean, they might just be saying that those two things are related to one another, that they are connected, or maybe associated. So specifically in statistics, we would say that the linear correlation coefficient r is a number that measures the strength and direction of a linear pattern for our data set. So we're looking at data that's not just related, connected, or associated, but connected and related in a linear fashion. And the correlation is going to tell us how strong that connection it is and what direction it is in. So the best way to get a feel for this at first is just to go ahead and look at some examples. So let's go ahead and do that. If you have an r equal to 1, that's what we call perfect positive correlation. So the strength of the correlation or the pattern is that it's perfect, perfectly linear. You could draw a line through that would actually hit all those points. And the direction is positive, meaning that it's an upward pattern. And if you have a negative 1, you'd think if 1 is perfect, maybe negative 1 is terrible, but no, negative 1 is also perfect. It's just a negative correlation means that we have a downward direction to our pattern. But again, it's still perfect. You could draw a line through that would hit all those points. As your linear pattern starts to kind of loosen up where it wouldn't be perfect anymore, but it's still strong, your values of r will drop off from 1 and negative 1 a little bit towards 0, but we're still very close to 1, still very close to negative 1 because our pattern is still very strong. You might notice at this point that the positive r is like a positive slope and the negative values of r go with a negative slope, and we'll see when we see the formula that that is not a coincidence. If your pattern starts to loosen up a little bit more, where there's still definitely an upward trend here and it's as linear as it is anything, I don't see it curving, it's just not real strong or tight. If I drew a line in, the misses or the errors or residuals are getting a little bit bigger. And with that, we're falling away from 1 and down to 0.8. And our r here is down to negative 0.8. And this is, again, the same strength as that one. It's just a downward direction. And if we continue on to the next page, we can see that trend continuing to change as the pattern loosens up some more. And we get what's almost just a blob with an upward trend and a blob with a downward trend. We see our correlation weaken to 0.419 and negative 0.419. In fact, this might even be a surprise to you. When you first look at this, it might seem like it's just a random mess, but there is a little bit of an upward trend, but not a lot. And so you might think, well, wow, 0.4, that's like right in the middle between 0 and 1, or almost in the middle. But keep in mind from the last section that if r was 0.4, then r squared would be 0.16, and that means that linear regression is only removing about 16% of the squared prediction error. So overdoing that horizontal prediction line versus the one here that would be just a little bit of an upward slant, you get an improvement, but not a big improvement. So keep that in mind when you see an r that's kind of in the middle, like a 0.4, that think about that r squared number, which would become closer to 0. And the same thing for this one, just a negative pattern. And then r that is close to 0 is kind of an interesting case because that can mean a couple very different things. If you have just a complete mess with no pattern whatsoever and no upward or downward trends, you can get an r of 0. But here we have another r of 0, and yet you look at this and this is not a mess at all. It's a perfect pattern. It's just that it's a perfect parabolic or quadratic pattern instead of a linear one. And we need to always keep that in mind, that our value of r is the strength of the linear pattern. And so if our pattern is a shape other than linear, that is not necessarily going to measure up using this r. And so we can't fall to the conclusion that when r is 0 that there's no pattern to the data. We can say there's no linear pattern. There's not a linear pattern here. There's not a linear pattern here either. So just keep that in mind, that r equals 0 can mean two very different things. Alright, so we've seen a few different pictures, so now let's try our skill with that and look at this picture and think about that question of, well, what R is this? So I'd like you to take a guess at that. Maybe just pause the video for a second and try and make a guess for what R is, but just a little bit of advice as you go to do that. Use the pictures that you've just seen. Maybe look back over the last page and this page and try and figure out where this fits in. You're not going to find it perfectly, so you're probably going to want to guess in between two of the values you've seen, and I would suggest just guessing to one decimal place. So go ahead and pause the video and take a quick guess there. Alright, so let me go ahead and show you the strategy I would use for guessing on this. The first thing that I notice is that this pattern is a downward pattern, and that means I'm going to guess something negative. It's not perfect, so it's going to be a decimal value. So negative 0 point something. So when I start looking at the ones that I have, I can look at this 0.419 and I can say, you know what, my pattern is not that bad. And I can look at the negative 0.806 and say my pattern is not that good. And in fact, I would say that the pattern is closer to this one than that one. So if I was going to guess to just one decimal place, I would say, well, it's not this good, it's not nearly that bad, so let me go just a little bit worse than this and guess like R is approximately negative 0.7. So that's what I think I would put there if I was just going to guess to one decimal place. If you had any guess that was between negative 0.8 and negative 0.4, I'd say you did a decent job of narrowing it down to the right range, and you shouldn't worry too much that if you didn't guess the exact same number. A negative 0.6, a negative 0.5 would also be good guesses as well. Just wrapping up that last example, it turns out that that one that I made a guess of negative 0.7, if you put that into Minitab, StatCrunch, into the calculator, something that could compute that correlation for you, it turns out that it's negative 0.729. So my guess was close. If your guess was negative 0.6, again, I would say that's close. You shouldn't feel bad about that at all. And you'll find that as you do more and more guessing, you get better and better at that. And we'll practice that when we get to our tech project. So don't worry about it if you're not real good at that right now, but it is something that we do want to try and continue to get better at. So we're going to go ahead and talk about how we interpret R in terms of different applications that we're working on. And I want to start out by just showing you the formula. Now the formula is quite messy, and don't be alarmed by that because we're actually going to use the calculator to calculate R every time that we do it. But the one thing that I wanted you to notice here, and it's just a quick mention, is that the denominator of this is positive, and if you were to look back at the denominator of our slope calculation, it was always positive, and the numerators of the two are the same. And so just the quick kind of takeaway from that is that this value of R and the value of slope are always going to have the same sign. So that thing that we saw in the pictures where the ones that were going upward had a positive correlation, just like the slope, is not a coincidence. The ones that were going down had a negative correlation, just like the slope. That's also not a coincidence. So when we go to interpret R, a few things to keep in mind. R is always going to be somewhere between negative 1 and 1. And remember, those are perfect correlations, both of them, one perfect positive, one perfect negative. And if R is close to 1, then there's a strong positive linear correlation between the variables. And if R is close to negative 1, then there's a strong negative linear correlation between the variables. And it's from those two lines that we get most of our interpretations. And just to kind of help you out a little bit here for homework and tests and collaboratives and stuff, when I ask people to interpret these, I expect them to say there's a strong positive, and I'm looking for that, but I'm also looking for the words linear and correlation. And also when you get to the variables part right here, you would want to specify what those variables were. So you'll see in a minute for the Mustangs, we'll talk about the age and the price, but you wouldn't just say a generic variables, you would mention what the variables were in the problem. And then the other thing that can come up as well is R might be close to 0, and then we would say the variables have weak, if any, linear correlation. But just a caution there, we saw this in the pictures. If R is close to 0, that doesn't mean that there's not any correlation at all. It means there's not linear correlation. Remember our kind of U-shaped parabolic data that has a perfect correlation, just not a linear correlation. Alright, so let's go ahead and see how this all would apply to the age and price data that we had for our Mustang GT convertibles. So here's that data set that we've seen before. and now they want us to determine the value of R. And I'm going to go ahead and show you how to do that on the calculator, and then we'll also interpret it as well. Let's see, go ahead and get this turned on. And when I'll go ahead and clear out of here. When you turn it on, you want to go into the Stat menu and Edit to enter in the data typically. I still have that data in from having done the linear regression and the R squared earlier. So you see that here already. If you don't have it in, I would suggest that you go ahead and pause the video and enter all the data into your calculator so you can try and follow along. And then once I have the data entered in, I want to do the same calculation I did back in section 4.2 for the linear regression. I'm going to press the Stat key. I'm going to go over to the Calc menu. I'm going to arrow down to number 8, which is our linear regression format. And I'm going to tell it where the data is, which is L1, L2. And I'm going to see the same screen I did before, which has my intercept and my slope, but it also has the values of R and R squared. If your calculator is not showing you that, make sure that you go back and look at the directions in section 4.3 for how to turn that feature on. But I'm getting my value of R, so I'm just going to copy that down from here. It looks like R is approximately negative 0.8844. So R is approximately negative 0.8844. And then they want me to interpret R in terms of the linear relationship between the variables. And so when I look at the possibilities here, that R is definitely close to -1, certainly closer to -1 than 0. And so I'm going to say there's a strong negative linear correlation. And up here it said between the variables, but as I mentioned up there, you always want to specify what the variables are. And on this problem, the variables were age and price. So I'm going to say there's a strong negative linear correlation between age and price. And it'd probably be a little bit better to mention for Mustang GT convertibles just to get better context. So before we move on, let me go ahead and just make a quick mention about what to do if your values of R are different than negative 0.88. This is pretty close to -1, so it felt pretty easy for me to go ahead and say that it was strong negative linear correlation. As the values fall off to like negative 0.7, negative 0.6, it can get more confusing. So at some point, as you get further and further away from the negative or positive one, you might want to start saying it's a moderate negative or positive linear correlation. If you drop down below 0.5 as 0.44, 0.32, something like that, you might start saying there's a weak negative linear correlation. There's no specific rules there, but just kind of have this idea in mind that the closer you are to 1 or -1, the stronger it is, and the closer you get to 0, the weaker the linear correlation is. And just taper your response that way. But again, there's no specific cutoffs that you have to follow. Another thing to keep in mind when you're talking about the linear correlation coefficient is that correlation does not prove cause. So even if there's a strong linear correlation between age and price for Mustang GT convertibles, that doesn't mean that the age itself is the cause for the Mustangs getting less expensive. It could be a factor. It could even be the main factor. It could even be a cause. But when you're doing an observational study and you get a strong correlation, you can only say that they're connected, they're correlated. You can't necessarily say one is causing the other. And in fact, I think for the cars that the age probably is not the main cause for why the price is going down. So go ahead and pause the video for a second and think about what do you think the main cause is for an older car costing less. So personally, I think that the reason older cars cost less is because they tend to get used up, and we usually say that that's measured by the wear and tear on the vehicle. And that's just a statement that says the car is getting used up as time goes by and therefore not as valuable. And what causes wear and tear? It's not necessarily age, though that can be a factor. If the car is left sitting out in the sun, then the sun could damage it. But then what's the real cause? I guess it's sun damage, not necessarily the age, but the sun damage takes time. Another thing that makes cars go down in value is that when they have more miles on them, people figure there's more wear and tear, and that reduces the value, but it takes time to put miles on. So even though time isn't the direct cause, it takes time for wear and tear to happen, and so it ends up having a strong correlation even if it's not the main cause of what's happening there with the price. And just an example to kind of help illustrate that, it turns out that there's a strong positive linear correlation between the number of Taco Bells a city has and the number of public restrooms it has. So does this show that Taco Bell restaurants are creating the need for more public restrooms? And if not, what lurking variable is a better explanation for this relationship? So we're not saying here that the Taco Bells themselves are causing the need for restrooms, but we're seeing that connection, and if you look this up, you would definitely see that connection. The lurking variable is a variable other than the ones that we're studying that is the true cause, and in this case, I think it's population. If you have a bigger town, there's going to be more Taco Bells, and there's also going to be more public restrooms. So we're seeing this connection between Taco Bell and the public restrooms. But maybe the real cause is down here lurking beneath, and that would be the population of the town that we're talking about. Bigger town, more Taco Bells. Bigger town, more public restrooms. So population is the driving factor on those, and that's what we call that lurking variable, but yet you would still see a really strong positive linear connection between the Taco Bells and the public restrooms themselves. So always keep that in mind. Even if you see a very strong positive or negative linear correlation, there might be some other variable that's lurking beneath that is the real cause of that relationship.